All right. Okay, I'm going to put this video together real quick for the Chapter 7 test review. On the first slide here is just kind of a list of all the things that we've covered and all the things that I'll cover in this video. Just to kind of split this apart, oh my gosh. This first topic is 7.1, where we write and solve exponential growth. Then we go 7.2. The next two topics are 7.3. This right here is 7.4. And then the last couple are whoops, nope, not what I want. The last couple are 7.5. So I'll put timestamps on here so you've got each section. But also, if you don't like how I explain stuff and want to go look for extra help out there, that's kind of a list of all the things that we've done in Chapter 7. The first one, just a single problem here. In Section 7.1, we did exponential modeling using the exponential growth equations. So, for example, the number of students at a local high school is increasing 3.5% per year. Currently 1,500 students enrolled at the high school. How many students will there be in 5 years? So obviously a couple numbers that are important here is this 3.5%. Remember, when we're doing exponential modeling, I want to change that 3.5% to 0.035. So that'll be my, that's the percent change as a decimal. I also have my start value, which is 1,500. That's our start value. And finally, we have the time that we're looking for. The amount of time we're looking for is in 5 years. What will the enrollment of the school be, or how many students will there be, basically? So I'm going to go ahead and set up an exponential growth equation, which is my start value. And remember, we always start with multiplying by 1. Since I'm growing, I'm going to use 1 plus. And then we're going to use this 0.035 here. And that's going to go into the parentheses to finish our growth factor. I'm going to raise it up to the 5th power. Okay, that's actually all we need to do for plugging stuff in. The rest of it can just be typed directly into the calculator. 1 plus 0.035 raised to the 5th power. Okay, and there we get a enrollment of 1781.52. Since we're talking students, we're going to round that to the nearest whole number. So about 1,782 students will be that population in 5 years. In 7.1, we also did graphing exponential equations, but we did graphing without any translations, so without any left, right, up, down. So I just saved that instead for the 7.2 problem, because if you can graph one that's got these translations in it, you can graph one that doesn't have translations in it. So the way we did this, right, we've got y equals -3 times 2 to the x plus 4. Because my start value is negative and my growth factor is bigger than 1, okay, again, a good way to think about this. If I'm starting at negative and I'm growing, the graph is going to look something like this. It's going to be one of those negative growth problems. So it's a good thing to know kind of just going into the problem so we can expect what the graph's going to look like, or at least a ballpark shape of what it'll look like. So what we did here is you could actually type the entire thing into the equation as it stands right now. But what I'm going to do is I'm going to move this up here. I'm going to take and plug in my calculator the parent function, which is just that -3 times 2 to the x. So I'll worry about the plus 4 and the plus 6 in just a minute. So with the parent function, I'm just going to go from -2 to 2, -2 to +2. And I'm going to let the calculator, again, do the work for me. So I got y equals -3 times 2 to the x. So I'm going to go here, negative 3 times 2 to the power of x. I'm going to go to the table now. Okay, and that gives me the y coordinates from negative 2 to positive 2. So I'm going to jot these down while they're here. So negative 0.75. You can see that those values are growing, right? They're all negative. But they are getting larger from negative 1.5 to negative 3 to negative 6 to negative 12. Okay, so this is what I have here, right there. Okay, and then I'm going to focus on the translations that we've gone on here. So here I have the plus 4, which is going to move everything left 4, which means the x coordinates are going to decrease. And we'll do it in a different color. Then I have this plus 6, which is going to move everything up 6, which means the y values are going to add 6. Okay. Again, you could type the entire function into the calculator, and I'm actually I don't want to do that just yet because I want to make sure I take these 5 points that we have and translate those 5 points. But I know if I'm going to take away 4 from the x's, take away 4 from each of the existing x coordinates. Okay, I could then go into the calculator and let the table do the work for me. I'm actually going to do that just to make sure I don't mess something up here. So I'm going to go ahead and in here alter this. So my exponent is x plus 4, and then I'm going to include the plus 6 on the outside. Whoops, didn't close off the parentheses. That would be bad. Okay, so there's my entire function. Now if I go to the table, okay, I have all these crazy big numbers, and you can kind of choose which values to use here. But because I started with the parent function, I know that I'm going to do from negative 6 to negative 2. So what I'm going to do is I'm going to copy those y coordinates from negative 6 to negative 2. So I'm going to copy those down real quick. It's 5.25, and then 4.5, and then 3, 0, and negative 6. Okay, so I'm going to come back here, and now I've got coordinates to graph. Okay. Negative 6, comma 5.25. 5.25 is about right there. Negative 5, comma 4.5. Negative 4, comma 3. Okay. Negative 3, comma 0. And negative 2, comma negative 6. So I can see that it's definitely falling very rapidly there. Another thing to take a look at is where is the asymptote going to be? We know that every parent function, right, this negative 3 times 2 to the x had, well, for this, the domain was all real numbers because I can plug in any number to an exponential function. But I see that I only have negative values, so the range would be y is less than or equal to 0. And the asymptote, the horizontal asymptote here was at y equals 0. Okay, so I'm just going to take those and adjust it for my the function that I'm looking for. Okay, since I'm subtracting 4 from all the x's and I'm adding 6 to all the y's, the domain was all real numbers, so it's still going to be all real numbers. What's important now though is that those y coordinates are also going to increase by 6. So my range is going to be y is less than or equal to 6 with an asymptote at positive 6. Again, it's a horizontal asymptote. So I'm going to go ahead and draw on that dashed line right across at 6. Okay, and so that way I know now. Should have done that in a different color, but I can now draw. This is not going to be pretty. Oh boy. Something that goes like that. Okay. And again, just make sure that asymptote is clear. that it is right there. So we can see that that line is approaching 6, but never quite gets there. So that was kind of the long way to go about that problem, but it does give us the parent function and then the transformations from there. So that was 7.2. 7.3, we did a couple different things. We first started by defining what is a logarithm, and we switched back and forth between logs and exponential functions. So this is exponential, and I know it's exponential because the variable is in the exponent. If I wanted to write this as a logarithm, I'd first have to get rid of that 5. So I'd divide by 5 on both sides. So give me 2.5 to the power of x equals 7. Now, when we talked about logarithms, every log has a base number, okay? And that base number matches the base of the exponent. The next is called the argument. I think I used the letter M. And that argument is the same as the answer in the exponential form. And then this is equal to, I don't know, we'll call it A. That might not be a good choice of, who cares, whatever. So those 3 things are going to go those 3 spots. So if I want to rewrite this as a logarithm, it would be log base 2.5 of 7 equals x. So this would be the log form of this expression, okay? So that's how we went from exponential into logarithm. Vice versa is then, of course, here's my base number raised to this power is equal to that expression. So 12 to the 4th equals 2x minus 3. I could go ahead and solve this then for x, because 12 to the 4th power it's a big number, but it's a number. If you're just asked to write it in exponential form, if you're asked just to write it in logarithmic form, that would be the end of it. Again, you could go ahead and solve for x. In this case, in this context, we weren't asked to, so we would leave it like that. That was the first thing we did in 7.3. And then because we knew what logarithms were, we wrapped up. We finished graphing. We finished with the last graphing piece in Chapter 7, which was to graph logarithmic functions that look something like this. Okay. So I have that function over here, and that's what we'll eventually get to. What I first want to do is build that logarithmic function from the inverse. I'm not going to use 5 cells here. I'm only going to use 3 rows of numbers. So I'm just going to get rid of these real quick. So if you recall the base of the logarithm, okay, so this thing is base 2. That means my entire function is going to come from y equals 2 to the x. So we're going to start with the exponential function y equals 2 to the x. I'm just going to pick the first or the easiest 3 numbers that come to mind. 2 to the 0 power is 1, 2 to the first is 2, 2 squared is 4. Just like in the last slide, we know that if I were to just graph that thing, the domain would be all real numbers. The range would be y has to stay above 0 because it's positive growth, and then the asymptote would be at y equals 0. The next thing we did was we said, okay, well, let's go to the inverse of that function, which is y equals log base 2 of x. And remember, with inverses, all we have to do is switch x and y around. Okay, so instead of 0, 1, this becomes 1, 0, 2, 1, and 4, 2. And this is the important part, and this is what we talked about in class, is that the domain and range then switch, right, because they're inverses, and we know that from previous learning. So then the domain would become x is greater than 0. The range would then assume the all real numbers, and the asymptote would become x equals 0 instead of y equals 0. Okay. And once we have the logarithmic, or once we have the log base 2 of x, now all I'm going to do is I see the x minus 4, which means I'm going to move to the right 4. Right 4 units, which means x is going to be added by 4. And I see that plus 3. I'm going to move up 3, so y is going to add 3. So if I do that for each of those values, add 4 to the x's. Oh, wait. Yeah, add 4, not add 5. Add 4 to the x's. And I'm going to add 3 to the y's, so it'd be 3, that'd be 4, that'd be 5. Okay. Remember that also, this change also messes with the domain. So this will be x is greater than 4. Still all real numbers for the range, but now the asymptote is going to be, I said 4, but wrote 0. X is equal to 4. Okay. So I'm going to graph those 3 coordinates in pink as well as the asymptote, and that will be enough to give us our graph. So x equals 4 as a vertical line straight down. Okay. And then we've got 5 comma 3, 6 comma 4, and 8 comma 5. 5 comma 3, 6 comma 4, and 8 comma 5. So that kind of gives us this downward sloping looking graph. 5, 3, 6, 4, and 8, 5. Yep. Okay, so that's kind of where we went with the graphing logarithms, building it from the exponential inverse that we have. Okay, that was 7.3. In 7.4, we learned about the 3 logarithmic properties, which allow us to split them up or condense them. So one thing we'll be asked to do here is to expand a logarithm. So we're going to take a single log with a lot of stuff in it and break it up into multiple things. In this case, I see there's precisely 4 items going on in here. I've got a 125, I've got x to the 8th, I've got 12, and I've got y to the 3rd, which means I'm going to have 4 logs here. Okay. So I'm going to do log base 5 of 125 plus, and I'm doing plus log base 5 of x to the 8th because this stuff was in the numerator. So any numerator things will be positive. Any denominator things will have a minus with it. So to finish this up, I'm going to have minus log base 5 of 12. That looks terrible. And minus as well. Even though they're anything in the denominator is going to have a subtraction because it's being it's part of the denominator. It's being divided. So I'm going to write this as log base 5 of y to the 3rd power. Okay. This is the first level of expansion. The other thing I can do is actually simplify any logs that have numbers that are whole numbers. I can simplify. So like this log base 5 of 125. Remember, that's basically saying 5 to what power gives you 125. So that's just 3. But then the other rule that we talked about is when you're expanding, we're talking full expansion, meaning any powers that you have to come out front. So that's going to change into plus 8 times log base 5 of x. Log base 5 of 12, I could change into a decimal, but I'm actually okay with you just leaving it like that. And then finally, this is minus, and I'm going to bring the 3 out front, minus 3 times log base 5 of y. Okay, so this is my fully expanded logarithm. I've split it up so each log only has a number or a variable with no powers. The flip side of that, of course, is to simplify or condense. So the first thing we're going to do is take basically in reverse order what we just did. I'm going to take powers and move them up to exponents here. So I'm going to have log base 4 of 25 to the 1/2 minus log base 4 of x plus log base 4 of y to the 7th power. Okay. The one thing I could do here is 25 to the 1/2. If you're the 1/2 power is the same as taking the square root. So this is basically saying log base 4 of the square root of 25. So I can just, it's still inside a logarithm. Okay, it's not equal to 5, the whole thing, but I can condense 25 to the 1/2 into just the number 5. So now I am ready to condense this into a single log. I am going to, one thing is a little weird, and that is that this minus logarithm is right in the middle. So just make sure you pay attention to the point that that log being negative means that's going to go into the denominator. Okay, so I'm going to go ahead and take care of that one right away. Since it's minus log base 4 of x, the x goes in the denominator, and then since the other two logs are positive, I'm going to take the 5 and the y to the 7th, and those two multiplied together will make up my numerator. Okay, so the positive logs make up the numerator, and the negative logs make up the denominator. Done there. Hooray. We move on. Okay, so 7/4 was expanding or simplifying. Our last section, and this is kind of the reason that we do all this stuff, is to be able to solve equations that have exponential functions in them or have logarithms in it. So I'm just going to buzz through a couple examples real quick of each. If I want to solve an exponential equation, okay, I need to isolate just the base and the exponent. So I want to get rid of the 7 and the 3. So I'm going to go ahead and add 7 to both sides. So I got 3 times 2 to the x plus 1 equals 33. I'm going to then divide by 3 to get rid of that start value. I get 2 to the x plus 1 equals 11. Okay, now that's written like this, I could either write that as a logarithm, like I could write it in logarithmic form, or I could just apply the log to both sides. So log of 2 to the x plus 1 is equal to log of 11. The reason I do that now is I can take this exponent and bring it out as a power. So x plus 1 times log of 2 is equal to log of 11. I'm going to go ahead and get rid of that log of 2 by dividing. Okay, so here my logs cancel out. I'm going to go to the calculator now for log 11 over log 2. Log 11 over log 2. And I get 3 point. At this point, this is where I'm going to round to the 10,000th or to 4 decimal points, only because logs, if you only round to 1 decimal point, it's really going to throw your answer off. So I'm going to say 3.4594. 3.4594. Okay. So what that gives me here is just x plus 1. So I'm going to take away 1 from both sides, and I get a value of x about 2.4594. Okay. Again, if you got time, like on a test or a quiz, take that answer, go back and plug it into x in the original equation, and you should get 26 on both sides. That's the nice thing about algebra and solving these equations, is you can always take a look at your final answer and make sure that it makes sense. Another type of exponential equation that we looked at was this, where it has common bases. So you could solve this problem with logs, and if you've asked me, I've probably shown you how to solve this problem with logarithms. But if I see that my bases are 27 and 81, another technique to do this is to write them. Those are both powers of 3. So what I can do is I can rewrite this as 27 is 3 to the 3rd power, and 81 is 3 to the 4th power, keeping everything else the same. But now that I have an exponent that's raised to another exponent, I'm going to go ahead and multiply my powers together. So 3 times 2x will be 6x, and then 4 times x plus 4. I do have to kind of distribute that 4. So this will be, this will be 3 to the 4x plus 16. Okay. Now that I wrote that equation as having the same base, I can essentially, since I know the bases are the same, I can drop those off and basically say, all right, well, now I need, if the bases are going to be the same, I need the powers to be the same. So I don't need the 3's anymore. I just need to solve this, and that's my solution. So 6x equals 4x plus 16. I'm going to take away the 4x from both sides. Then I have 2x is equal to 16. Divide that by 2 on both sides, and x is equal to 8. Okay. So again, I could go back and plug in 8 for x, and I should get the same thing on both sides. Okay. So that was just another method to solving the exponential equations. And then finally, the last thing we did in 752 was solve equations that have logarithms. And basically, it comes down to, if it's a single logarithm, we're just going to write it in exponential form and then solve what we have from there. So if I don't see a base, we know that's base 10. So to write this into exponential form, it would be my base raised to that power, which is 10 to the second, equals the argument. So x over x minus 8. Okay. 10 squared, that's 100, equals x over x minus 8. This is kind of a tricky one because I've got x on both top and bottom. Please don't try to cancel these out and just call it 100 equals 8. I also can't simplify. I can't break up this fraction at all because the denominator is kind of goofy. And we'll talk about that more in chapter 8. So what I'm going to do is I'm going to multiply both sides of this equation by x minus 8. Okay. And what that allows me to do is that does allow me to take this x minus 8 and cancel that x minus 8. So now I don't have any fractions anymore. All I have is this left side, which I have to distribute, that 100, and that will equal x. Okay, so if I distribute the 100, I have 100x minus 800 equals just x. Okay, so it's kind of goofy, kind of a weird equation. I have x on both sides technically, so I need both x's to be on the same side. I'm going to go ahead and take away 100x. Okay. One thing, if you want to put the 1 in front to remind yourself that that is 1x. When I take away 100x from that, then 1 take away 100 is negative 99x. I'm then going to divide by negative 99. Divide by negative 99. This is going to be a goofy answer, but again, I'm just going to round to the nearest 10,000th place. So I'm going to do negative 800 divided by negative 99. You could also leave it a fraction, but 8.0808. Repeating, it looks like. So I'm going to write it as x is 8.0808. Okay. So there's my log equation. That is my one solution that log equation has. Again, kind of a little goofy and kind of an odd answer, but make sure just write it into exponential form and then start to solve. The key here was that I had a fraction on the right side, but then I multiplied both sides by the denominator in order to get rid of the fraction itself. So that's probably the most important step to that problem. Finally, we'll wrap this up. How do I solve a logarithmic equation if I have multiple logs in it? So what I'm going to do here is the first thing I need to do is concern myself just with the left side of this equation. I can't solve this if it's multiple logs, so I need to first use what we learned from 7.4 to condense this down into one log. So I'm going to take the 2 and send that up top. So this is log base 4 of x squared plus log base 4 of 3 minus log base 4 of 6 is equal to 3. Now then, since they're all log base 4, I'm going to build this fraction. I've got 2 positive logs right here. So that means my numerator is going to be 3x squared. And I have 1 negative log, obviously right here. So 6 is going to be my denominator. And then this is equal to 3. Okay. So the first thing we need to do is write it as a single log. Now I'm going to go ahead and solve this. So I'm going to write it in exponential form, which means my base 4 to the 3rd power is equal to this fraction 3x squared over 6. 4 to the 3rd is 64. Again, if I've got a fraction, I'm going to multiply both sides by the denominator, so times that by 6. There's a couple other ways you could attack this, but I'm going to do this. 64 multiplied by 6, that's at 33. It should be 384. 64 times 6, 384. So we come back here. I got 384. Those cancel, is equal to 3x squared. I'm then going to divide by 3 on both sides. I should know what that is. Divided by 3, it's 100 and something, 28. So I got 128 is equal to x squared. Finally, to wrap this up, I'm going to square root both sides. Okay. When I square root both sides, the square root of 128 is the key here is that even though the calculator is only going to give me positive 11.3137. Since I'm square rooting, I do need to remember that this is technically plus and minus. Oh God, I already forgot. 11.3137. Okay. What's kind of nice about these log equations is I can't take the log of a negative number. And if I look up here, the original question did just ask me to take the log of x. And because that was the way it was originally written, I can't have a negative x value. So that means I do have an extraneous solution. So even though this says plus or minus, truly the only value that can work is 11.3137. And I'm sure some of you may have seen a controversial thing about this. And we can have an argument about that last statement, why negative 11.3137 doesn't work, if you want to. But we're going to just go with the positive value for that. So kind of a rundown. I know it took a little while, but again, since it's a review, my thought is to kind of hit on everything. Again, this is the list of topics that we covered. Okay. Go back to the beginning quick. So those are those 5 sections. Please make sure that you're able to do all of these things. And if you're not sure, then definitely come in and ask for some assistance and we can look at helping you out. For now, I'm going to log off. We'll see you next time.